Well, hi everybody and welcome to my channel Art and Physics. In today's video we will solve a very interesting problem which also hides a commonly overlooked subject. Well, the system that we will analyze is shown on the screen, and it basically consists on a bar which can rotate through an axis, through a vertical axis, with a constant angular velocity equal to omega. There is also a mass m that can move through the bar and is connected by means of a spring to a fixed point, the point O. This spring has a stiffness K, and we will assume that the natural length of the spring is 0. And also we will assume that the system is completely frictionless, so there is no friction in the system. So the question here will be to find or to analyze the speed of the mass in terms of the position of the mass along this bar. So in order to answer this question, we first here will write the Newton's second law of motion, and according to the symmetry of this problem, we will use this Newton's second law in polar coordinates. So first I will draw here the free body diagram of the mass. So if we have the mass here, this is our mass m. The forces acting on the mass are the following. Well, first is the gravity, vertical pointing downwards. There is the force exerted by the spring. I will call it Fr. And also there is the normal force, the vertical normal force, n theta. I will call it n theta. And an additional normal force, a transversal normal force, which is exerted from the bar to the mass. I will call this force n sub theta. This is a 3D version of the free body diagram. We can also note here that the force exerted by the spring is just simply the stiffness of the string, K, times its deformation, which is rho. And I will use the Greek letter rho in order to denote the distance of the mass to the origin of the system, which is also the point O. The point O will be our origin of our system. Theta will denote, in this case, the rotation of this bar. So, according to this free body diagram, we can write the Newton's second law as following. In the radial direction, we have the component of the total force acting on the mass in radial direction is minus k rho, y minus, because this force is pointing to the origin of the system. So this force should be equal to the mass m times the acceleration of the mass in radial direction, which in polar coordinates is rho double dot minus rho times theta dot square. In this case, theta dot is just omega, so we have omega square. In transversal direction, the Newton second law is written as n sub theta equals the mass times the acceleration in transversal direction written in polar coordinates, which is 2 times rho dot times theta dot, which is omega, plus rho times theta double dot. Well, in our case, the system is rotated with constant angular velocity, so theta double dot is 0. This term vanishes here. And the third equation in vertical direction is, well, very simply, it's just n sub theta equals mg. Well, strictly speaking, we are using cylindrical coordinates, but the third equation here will be not much important for us. The important equation for us are the equation 1 and 2. I will anyway call this one equation 3. So these are the equation that we can write from the Newton's second law. Okay, and we will center our attention now in the equation number 1. we can do the following thing here. We can integrate the equation number 1, remembering that rho double dot, which is the derivative or rho dot in time, can be written, well, this is basically chain rule, as follows. In other words, rho double dot is equal to rho dot times d rho dot over d rho. And this later expression will help us to solve the equation number 1. We can plug this result in the equation number 1 as follows. Okay, this is simply substituting this expression in the equation number 1. And this resulting equation, this resulting differential equation, is now the differential equation we can solve using the separate variables. If we take all the rho in one side of the equation and rho dot in the other side, we can write this later equation as follows. Rho d rho like that. Okay, so we can integrate this equation. Worth to mention, I forgot to mention, but it's important. We will assume that that the initial condition of this system, in the initial condition, the mass m is in the point O, and an initial given velocity is given to the mass m. This velocity will be an initial radial velocity, which we will call b sub 0. In the initial in t equals 0, the radial velocity of the mass is b sub 0, and the mass m is located in the point O. In other words, if we integrate this later equation, we will use the following: rho d rho, and the limits of integration of this integral, which is written in terms of rho, comes from 0 to some rho, some distance of the mass to the point O, and this will be equal to the integral of m rho dot d rho dot from the velocity, the radial velocity that this mass has in t equals 0, which is b 0, to some arbitrary velocity, radial velocity rho dot. These integrals are quite simple. Simply the result will be 1/2 times m omega square minus k rho square. In this case, is the upper limit will appear here. The lower limit is just 0, and in the right hand side we will have 1/2 m rho dot square minus 1/2 m b 0 square, which this later equation can be rearranged and written as follows: 1/2 k rho square plus 1/2 m rho dot square should be equal to 1/2 m omega square rho square plus 1/2 m times b0 square. So important, very important result. I will draw my classic red rectangle here. We will call this equation the equation number 4. Okay, it's an important result again, which was obtained from the Newton's second law in radial direction here. Okay, so if we look closely to this equation, some terms are very familiar here, and it seems that the conclusion that we had reached here in this equation, it looks somehow like the conservation of mechanical energy. In particular, in the left side of the equations appears this term 1/2 k rho square, which is simply the elastic potential energy stored by the spring. And this expression, this 1/2 m rho dot square, looks very, very similar to some kinetic energy. So we can solve this problem using another approach. We can verify if we directly apply the conservation of mechanical energy. We should, at first, in principle, reach to the same conclusion as in equation number 4. Okay? Because, remember, there is no non-conservative forces. There is no friction. So the mechanical energy should be conserved. Okay? So let's do this calculation. I will make another drawing here. I will draw the mass in their initial condition, t equals 0. In the initial conditions, rho is 0. And the velocity is radial velocity base of 0. Thus, we have no potential elastic energy. I will call it U sub E, is 0. And the kinetic energy is 1/2 m v0 square. And in the final condition, this is initial, this is final, and some arbitrary time is t. Well, rho is just simply rho. And we have here two velocities, a radial velocity, given by rho dot, and a transversal velocity, which is given by rho times theta dot, which is omega. So in this final configuration, the elastic energy is 1/2 k rho square. Remember that our assumption is that the spring has a natural length equal to 0, so the deformation in this case is just simply rho. And the kinetic energy can be written as 1/2 m rho dot square plus 1/2 m rho square omega square. Okay, perfect. So this is the initial energy, and the energy in times t equals 0, and this is the final energy, the sum of the elastic plus the kinetic. There will be no change in gravitational potential energy, so it will not bother us to include the gravitational potential energy because it simply did not change. The mass moved at a constant height in a horizontal plane. So initial energy is equal simply to the sum of U sub E plus T. In this case, it's just simply 1/2 m v0 square, and the final energy is the sum of the elastic potential stored by the spring and the final kinetic, which is simply 1/2 m rho dot square plus 1/2 m rho square omega square plus 1/2 k rho square. And the variation of mechanical energy is equal to the final minus the initial, will lead us to the following result. Minus the initial equals 0. Remember, at first this is perfectly fine because there is no non-conservative forces acting on the mass. And this later equation can be also rearranged in order to produce some similar result to that we obtained from the Newton's second law, as follows. Okay, I just simply pass some terms from one side to another of the equation, and if we rearrange, then we can then obtain this equation that I will also put inside a red rectangle here. Okay, perfect. And if we compare this equation that we obtained from conservation of mechanical energy to the equation that we obtained from the integration of the Newton's second law, we can we note that are very similar. In principle, are very, very similar, but they are not the same. They are not the same. The only terms that differs here between these two equations is this one and a half m omega square rho square appears here in the right hand side with a plus sign, but in this other equation appears with a minus sign. So what is happening here? What is the problem? Is this physics broken? Well, of course not, at least in mechanical and classical physics. No, I don't know what is happening in some stuff with quantum mechanics, but in classical mechanics all is working good. The problem is not physics. The problem is that in this case there are forces that are doing work, non-conservative forces that do work, that perform work. What is this force? Remember, there is no friction. In this case, there is a restriction force. There is a normal force that is performing work. And if we remember from our first courses of physics, the most common thing is that the normal force do not exert work because they act perpendicular to the motion of the particle. But in this case, that will not happen. Let's imagine the following. Let's suppose that we are looking at our system from above. Okay, so I will draw here. I will draw the coordinate system. This is our point O. And if we imagine the trajectory that the mass m will follow from above, it will look like, I will draw it in red, it will look like somehow like a spiral. Okay? At first is in the point O, and it will continuously traveling away from point O. Okay? And I will draw here the bar. In some arbitrary position, the bar will be located like so, and white is better. Okay, and I will draw also with green color the normal n sub theta, this transversal, this force exerted from the bar to the mass. This force is perpendicular to the bar, but if we look closely, if we analyze this closely, we can note that the displacement of our mass, of our particle, is not perpendicular to normal force. Which in this case, in this drawing, I exaggerate in order that you can visualize very clearly. But we can reach the same conclusion if we analyze the following: the velocity of the particle, the mass m, which is simply the rate of change of their displacement with respect to time, in polar coordinates is written as rho dot in the radial direction, rho hat, plus rho times theta dot, which is omega, in the transversal direction. Okay, this is the velocity. In other words, the elemental displacement of the mass, this dr, is equal to rho dot dt in direction of radial plus rho omega dt in direction of transversal. And I will write again here the second equation that we obtained from the Newton's second law, this equation in transversal direction, which says the following. It says that n sub theta is equal to 2 times m times rho dot omega in direction of theta dot. These two equations, these two expressions mean the following: the normal n sub theta and the elemental displacement both share a common component in theta hat in the direction, in transversal direction. So their dot product is not zero. In other words, in physical terms, the normal force n sub theta is performing work. As a matter of fact, the elemental work in this case is written as n sub theta. I will use the arrow notation in order to indicate that this is actually a vector, times dr, dot product, which is in our case will be equal to 2m rho dot omega times rho omega dt. Okay, this is not zero now. And we can also break this, remembering that rho dot is d rho over dt, as follows: 2m rho omega square d rho. This is the expression for the elemental work performed by the normal n sub theta. So the total work performed by this normal force, but this restriction force, will be equal to the integral, the sum, of these elemental works from a rho 0 to some rho of 2m rho omega square d rho. And this work will simply, in this case, will be equal to m omega square rho square. And now we can correct our equation that we obtained from the conservation of mechanical energy, because in this case, in this problem, mechanical energy is not being conserved, because there is this restriction force which is performing work. So we shall use the following version of the conservation between cost of mechanical energy. The variation, the change of mechanical energy, is equal to the work done by the non-conservative forces. And if we use this equation, we can read this as follows. Well, here above I brought the expression for the change in mechanical energy. I have it here. It's 1/2 m. I will write it again. Okay, this is it. This is the change of mechanical energy. But now it's not equal to 0. It's equal to the work done by this restriction force, which is m omega square rho square. And now, if we rearrange and we simplify this expression, we reach to the following conclusion. These two terms are important. This and this I will pass this first term, 1/2 m omega square rho square, to the right hand side of our equation, and will appear now with a plus 1/2 as 1 minus 1/2 plus this 1/2 m b0 square. Okay, I will also draw a big red rectangle here. And if we are now compare this result with the result that were obtained from the Newton's second law, now we know that both are the same. Okay, so what is the importance of this problem? It's the following. The most common case is that the restriction force do not perform work, but the most common case is that normal forces are perpendicular to the direction of motion of the particle, of all the bodies, so they do not perform work. But this is not always the case. There is some system in which the normal force actually exert work, and this is one very good example of that. Okay, so I want to upload this video in order to you to know that some rules are not actually rules. There are things that are very common, are very happens very usually, but there are some cases in this and that is not true. Okay, so we conclude then that the physical is not broken. Mechanical energy, the conservation of mechanical energy in this case is not zero, because again there is some restriction forces that is performing work. Okay, so well, that's the video of today. I hope you enjoy it. If you have any question, you can make question in the comment section. I will try to respond all the question, and if you like the video, give a like, and if you like a lot, a subscribe also will be very much appreciated from you. Okay, that's all for now. See you in the next video. Bye bye.